Imagine waking up one morning, stepping outside, and seeing the sky painted in colors you've never witnessed before. Brilliant greens, deep purples, and shimmering reds dance across the horizon, not just at the poles but everywhere. Beautiful, right? Now imagine that same sky slowly killing everything around you. 42,000 years ago, something catastrophic happened to Earth. Something so powerful, so unprecedented, that it may have rewritten the fate of humanity itself. The magnetic field that shields our planet, the invisible force field protecting us from the sun's deadly radiation, didn't just weaken. It nearly vanished. For several centuries, Earth was left naked and vulnerable in the cosmic shooting gallery of space. They call it the Adams Event, named after science fiction writer Douglas Adams, who famously claimed that 42 was the answer to life, the universe, and everything. But there's nothing funny about what happened 42,000 years ago. This wasn't just another chapter in Earth's geological history. This was an extinction-level event that pushed multiple species over the edge, transformed entire ecosystems, and may have wiped out our ancient cousins, the Neanderthals. Scientists discovered evidence of this catastrophe buried in ancient tree rings from New Zealand kauri trees, trees that had been perfectly preserved in wetlands for tens of thousands of years. Inside those rings, they found a story written in carbon isotopes, a story of cosmic chaos that coincided with one of the most mysterious periods in human prehistory. During the Adams Event, Earth's magnetic field dropped to just 6% of its current strength. Solar winds, streams of charged particles constantly flowing from the sun, began penetrating our atmosphere directly. The ozone layer deteriorated. Cosmic radiation levels skyrocketed. Lightning storms became more frequent and intense, and those breathtaking auroras. They weren't just pretty lights. They were visible warnings that the very fabric of Earth's protective shield was tearing apart. But here's where it gets truly chilling. This event perfectly aligns with the disappearance of Neanderthals, the extinction of Australian megafauna, the mysterious decline of cave art in Europe, and dramatic climate shifts that plunged the world into chaos. Coincidence? Scientists don't think so anymore. For years, we've wondered what really happened to the Neanderthals. They survived ice ages. They made tools, created art, and adapted to some of the harshest conditions imaginable. They weren't primitive brutes. They were intelligent, resourceful humans who shared 99.7% of our DNA. So what finally pushed them into extinction around 40,000 years ago? The answer might not be on Earth at all. It might have come from space, delivered by a weakened magnetic field and a sun that suddenly became a mortal enemy. The Adams Event wasn't just a geological curiosity. It was a cosmic storm that transformed our planet, altered the course of evolution, and possibly gave Homo sapiens the competitive edge we needed to become the last humans standing. This is the story of humanity's closest brush with extinction that you've never heard about. This is the story of the Adams Event. Right now, as you're reading this, you're being protected by something you can't see, can't feel, and probably never think about. It's been guarding you since the moment you were born, and it's been protecting life on Earth for billions of years. I'm talking about Earth's magnetic field, an invisible bubble of magnetism that extends thousands of miles into space, deflecting solar radiation and cosmic rays that would otherwise sterilize our planet. Think of it as Earth's force field, like something out of Star Trek, except it's completely real. And here's the terrifying part. It's not permanent. It flickers. It weakens. And sometimes it disappears entirely. To understand what happened during the Adams Event, we first need to understand what we're dealing with. Earth's magnetic field is generated deep below our feet, about 1,800 miles down, in the outer core of our planet. Down there, liquid iron, heated to thousands of degrees, swirls and flows in massive currents. This movement of electrically conductive molten metal creates electric currents, which in turn generate magnetic fields. Scientists call this the geodynamo, and it's been running like a cosmic generator for over 3 billion years. the magnetic field it produces isn't just some abstract scientific concept. It has real, tangible effects on our daily lives. It's what makes compasses work. It's what creates those spectacular auroras, the northern and southern lights, when charged particles from the sun interact with our magnetic field near the poles. But most importantly, it's what keeps the solar wind from stripping away our atmosphere, the way it stripped away Mars's atmosphere billions of years ago. Mars used to have a magnetic field. Then it died. And when it died, the sun slowly peeled away the Martian atmosphere like removing the skin from an orange. Today, Mars is a barren, radiation-blasted wasteland with an atmosphere so thin you could barely fly a helicopter in it. That's what happens to a planet without magnetic protection. But here's where things get really interesting and really unsettling. Earth's magnetic field isn't stable. It's constantly shifting, fluctuating in strength and direction. The magnetic North Pole, for instance, isn't fixed. It wanders. In fact, it's currently moving from Canada towards Siberia at a rate of about 34 miles per year, and it's accelerating. GPS systems and navigation charts have to be constantly updated to account for this drift. Even more dramatic, geological records show that Earth's magnetic field completely flips every few 100,000 years. North becomes south, south becomes north. These are called geomagnetic reversals, and they're a normal part of Earth's magnetic cycle. The last full reversal happened about 780,000 years ago, an event called the Bronhes-Matuyama reversal. But reversals aren't smooth transitions. They don't happen overnight. The process can take thousands of years, and during that transition period, something very dangerous occurs. The magnetic field weakens dramatically, sometimes dropping to just a fraction of its normal strength. Occasionally, the field weakens and wobbles, but doesn't complete a full reversal. Scientists call these events excursions, temporary dramatic weakening and instability of the magnetic field. And that's exactly what happened 42,000 years ago during the Lachamp excursion, the event now known as the Adams event. The Lachamp excursion lasted for roughly 1,000 years, but the period of extreme weakness, when Earth's magnetic field dropped to just 6% of its current strength, lasted for several centuries. To put that in perspective, imagine your house's security system going from full strength to barely functioning. Suddenly, everything that was kept out can now get in. When Earth's magnetic field weakened to 6%, the protective bubble that normally extends about 40,000 miles into space collapsed to a fraction of that distance. Solar wind particles that would normally be deflected harmlessly into space began penetrating deep into Earth's atmosphere. Cosmic rays from distant supernovae and exploding stars, rays that are normally blocked, suddenly had a direct path to Earth's surface. The consequences were immediate and catastrophic, but they didn't happen in an obvious Hollywood disaster movie kind of way. There was no single moment of destruction. Instead, Earth entered a prolonged period of environmental chaos that unfolded over centuries, touching every ecosystem, altering weather patterns, and creating conditions that would test every species' ability to survive. But here's the question that haunted scientists for decades. How do we know this actually happened? We're talking about an event that occurred 42,000 years ago, long before written history, long before recorded observations. How can we possibly know what Earth's magnetic field was doing back then? The answer lies buried in the most unlikely place: ancient trees preserved in New Zealand swamps. And the discovery of these trees, and what they revealed, changed everything we thought we knew about this period in Earth's history. In the early 2000s, construction workers in New Zealand were digging in the wetlands near Ngawa Springs when they hit something unusual: massive tree trunks buried deep in the mud. Not just one or two trees, but entire ancient forests, perfectly preserved, as if they'd been frozen in time. These weren't just any trees. They were kauri trees, giant conifers native to New Zealand that can live for over 2,000 years and grow to heights of 150 feet. But these particular trees had been dead for a very, very long time. When scientists examined them, they discovered something extraordinary. These trees had died approximately 42,000 years ago, and they had been preserved so perfectly that their wood was still intact, their tree rings still visible and readable. For scientists, this was like finding a time capsule. Tree rings are nature's historical record. Each year, a tree adds a new growth ring, and embedded in those rings is information about the environment during that year: temperature, rainfall, and most importantly for our story, atmospheric carbon levels. You see, trees absorb carbon dioxide from the atmosphere as they grow, and that carbon becomes part of the wood structure. But not all carbon is the same. There are different isotopes of carbon, including carbon-14, also known as radiocarbon. Carbon-14 is constantly being created in Earth's upper atmosphere when cosmic rays from space collide with nitrogen atoms. Under normal circumstances, the production rate of carbon-14 is relatively stable because Earth's magnetic field keeps most cosmic rays at bay. But what happens when the magnetic field weakens? More cosmic rays get through, and when more cosmic rays penetrate the atmosphere, more carbon-14 gets produced. This leaves a detectable signature in anything that absorbs atmospheric carbon, including trees. When scientists from the University of New South Wales, led by Professor Chris Turney, analysed the tree rings from these ancient kauri trees, they found something shocking. Around 42,000 years ago, there was a massive spike in atmospheric carbon-14 levels, not a small fluctuation, a huge, sustained increase that lasted for centuries. This could only mean one thing: Earth's magnetic field had collapsed during that period, allowing cosmic radiation to flood into the atmosphere at unprecedented levels. The trees had recorded the Adams event in their rings like a cosmic dosimeter, measuring the radiation exposure our planet had endured. But the team didn't stop there. They wanted to understand what this actually meant for life on Earth. So they built computer models to simulate what happens to Earth's atmosphere when the magnetic field drops to 6% of normal strength. They partnered with climate scientists, atmospheric physicists, and paleontologists to piece together the full picture. What they discovered was far worse than anyone had imagined. When the magnetic field weakened, the sun became a much more dangerous neighbor. Our star constantly emits what's called the solar wind, a stream of charged particles flowing outward in all directions. Normally, Earth's magnetic field deflects these particles around our planet, like water flowing around a rock in a river. The particles that do get through are funneled toward the magnetic poles, where they create the beautiful auroras we occasionally see in the far north and south. But during the Adams event, with the magnetic field at just 6% strength, those particles weren't being deflected effectively. They were penetrating much deeper into the atmosphere, and they were doing it all over the planet, not just at the poles. The models showed that auroras, those shimmering curtains of light normally confined to Arctic and Antarctic regions, would have been visible across the entire globe during the Adams event. Imagine standing at the equator and seeing the sky light up with green and purple waves every night. Beautiful? Absolutely, but also a visible warning sign that Earth's protective shield was failing. And it wasn't just the auroras. The increased cosmic radiation had a cascade of effects throughout the atmosphere. It ionized air molecules, creating electrical instability that led to more frequent and more intense lightning storms. It damaged the ozone layer, that crucial atmospheric barrier that protects life from harmful ultraviolet radiation. As the ozone thinned, UV exposure at Earth's surface increased dramatically. The research team published their findings in the journal Science in 2021, and the implications sent shockwaves through the scientific community. This wasn't just an interesting geological curiosity. This was evidence of a genuine environmental catastrophe that coincided with some of the most dramatic changes in human prehistory. The timing was too perfect to be coincidence. Around 42,000 years ago, the exact period of the Adams event. Multiple significant events occurred across the planet. The extinction of Neanderthals in Europe, which had puzzled anthropologists for decades, cave paintings in Europe suddenly changed in style and frequency, suggesting cultural or environmental disruption. Megafauna in Australia went extinct, including giant wombats, marsupial lions, and enormous kangaroos. Climate records show sudden dramatic cooling events and shifts in weather patterns. For years, these events had been studied separately, with researchers proposing various explanations for each one. Maybe Neanderthals were outcompeted by modern humans. Maybe Australian megafauna were hunted to extinction. Maybe climate change was driven by volcanic activity or natural cycles. But now there was a unifying thread connecting all of these events, the Adams event. A cosmic catastrophe that had touched every corner of the planet and left evidence not just in tree rings, but in ice cores from Greenland, cave sediments in Europe, and archaeological sites across multiple continents. The ancient kauri trees from New Zealand had revealed a secret that had been hidden for 42,000 years. Earth had been vulnerable, exposed to cosmic forces that normally stay safely beyond our magnetic bubble. And during those vulnerable centuries, life on Earth had been tested in ways we're only now beginning to understand. So what did Earth actually look like during the Adams event? What would you have experienced if you were alive 42,000 years ago, wandering the landscape as either a Homo sapiens or a Neanderthal? First, let's be clear about one thing: this wasn't a sudden apocalypse. Hollywood has conditioned us to expect disasters to be dramatic and immediate. Asteroids crashing down, supervolcanoes exploding, tidal waves sweeping across continents. The Adams event wasn't like that. It was a slow-motion catastrophe unfolding over centuries, with effects that would have been subtle at first, but increasingly impossible to ignore. The sky would have been different, not every day, but frequently enough to become part of normal life. Remember those auroras? During the height of the magnetic field collapse, they would have appeared regularly, even at low latitude. Indigenous peoples around the world have oral traditions about sky fires and unusual celestial phenomena. Some researchers now believe these stories might be cultural memories of the Adams event, passed down through hundreds of generations. But the auroras were just the visible symptom of something far more dangerous: radiation exposure. With cosmic rays penetrating deep into the atmosphere and the ozone layer degraded, UV radiation at Earth's surface increased significantly. This would have had immediate biological consequences. Plants, which are particularly sensitive to UV radiation, would have experienced stress. Increased UV damages DNA and disrupts photosynthesis. In the computer models created by the research team, vegetation patterns shifted noticeably during the Adams event. Some plant species would have retreated to shaded areas or higher latitudes. Others might have developed protective pigments, making forests look different, perhaps darker or more colorful than they had been before. Animals dependent on those plants would have felt the pressure. Food sources would have become less reliable. Migration patterns would have shifted, and at the top of the food chain, predators, including humans, would have found their prey behaving differently, moving to new territories or declining in numbers. The electrical effects were equally dramatic. When cosmic rays ionize the atmosphere, they create more pathways for electrical discharge. This means more lightning, more frequent storms, and more intense electrical activity. Fire would have become a more constant presence on the landscape. While lightning-caused fires are natural and even beneficial in some ecosystems, the increased frequency during the Adams event would have been disruptive, burning areas that normally stayed green and wet. Ancient humans were already comfortable with fire. They'd been controlling it for hundreds of thousands of years, but dealing with more frequent natural fires would have required adaptation. Caves that had been safe shelters might suddenly become death traps if fires burned nearby. Hunting grounds could turn to ash overnight. Water sources could become contaminated with ash and debris. The climate effects were perhaps the most far-reaching. Increased cosmic radiation doesn't just affect biology and electricity, it also influences cloud formation. Cosmic rays act as seeds for cloud droplets. More cosmic rays mean more clouds. More clouds mean Earth's albedo, its reflectivity, increases. More sunlight gets reflected back into space. And when more sunlight is reflected away, temperatures drop. The geological record from this period shows exactly that, significant cooling events that coincided with the Adams event. Ice cores from Greenland reveal rapid temperature drops. Lake sediments show changes in the types of pollen deposited, indicating that forests were shifting toward cold-adapted species. Ocean sediments reveal changes in plankton populations consistent with cooling waters. But it wasn't a uniform global cooling like an ice age, it was chaotic. Some regions cooled dramatically, while others experienced drought. Weather patterns became unstable and unpredictable. Monsoon systems, critical for water supply in many regions, weakened or shifted. Growing seasons shortened, frost came earlier and lasted longer. For early humans living close to the edge of survival, these changes would have been devastating. Imagine depending on seasonal fruit harvests, only to have frost kill the blossoms. Imagine following migrating herds, only to find they've changed their routes. Imagine knowing where to find water year after year, only to have those sources dry up. And through all of this, there was another invisible threat: the radiation itself. While Earth's atmosphere still provided significant protection, we're not talking about radiation levels that would cause immediate radiation sickness. The increased cosmic ray exposure over decades and centuries would have had cumulative effects: higher mutation rates in offspring, increased cancer rates, reduced fertility in some populations, weakened immune systems, making communities more vulnerable to disease. These effects wouldn't have been obvious or immediate, but they would have added to the stress populations were already experiencing from climate disruption and resource scarcity. The archaeological record from this period shows something fascinating and troubling: a notable decrease in human population diversity around 40,000 years ago. Genetic studies of modern humans reveal what scientists call a bottleneck, a period when human populations decline significantly, reducing genetic diversity in ways that are still detectable today. We're talking about a time when humanity nearly didn't make it, when the total global human population might have dropped to tens of thousands of individuals, scattered across Africa, Europe, Asia, and Australia, all struggling to adapt to a planet that had suddenly become more hostile. Some populations succeeded, they adapted, moved, found new resources, developed new technologies and strategies. They survived the Adams event and went on to populate the entire planet, eventually developing agriculture, building civilizations, and creating the modern world. But other populations didn't make it, and among those who failed to survive this cosmic catastrophe were our closest relatives, the ones who had walked alongside us for hundreds of thousands of years, who shared our intelligence and our capacity for culture and tool-making. The Neanderthals. Their disappearance from the archaeological record happens right in the middle of the Adams event timeline. And that's not a coincidence. For billions of years, the sun has been Earth's benefactor, the source of warmth, light, and energy that makes life possible. Every plant, every animal, every human being owes its existence to that massive ball of nuclear fusion, 93 million miles away. We worship it, we celebrate it, we build our entire lives around its daily journey across the sky. But during the Adams event, the sun became something else entirely. It became a threat. Here's what most people don't realize about our relationship with the sun: it's only safe because we're protected. The sun isn't just sending us gentle, life-giving light. It's constantly bombarding us with deadly radiation, high-energy particles, and electromagnetic fury. Every second, the sun releases the energy equivalent of billions of nuclear bombs through the process of nuclear fusion in its core. That energy radiates outward in all directions, and a tiny fraction of it reaches Earth. Under normal circumstances, we're fine. Earth's magnetic field deflects most of the dangerous particles. Our atmosphere absorbs most of the harmful radiation. The ozone layer filters out UV rays that would otherwise sterilize the surface. We've evolved under these protective layers. Our DNA, our cells, our entire biology is calibrated for life under Earth's triple defense system: magnetosphere, atmosphere, and ozone layer. But when the magnetic field collapsed during the Adams event, that triple defense became a double defense, and that made all the difference. Let's talk about what actually happens when charged particles from the sun hit Earth's magnetic field. Under normal conditions, the solar wind, that constant stream of protons and electrons flowing from the sun, encounters our magnetic field about 40,000 miles above Earth's surface. The field deflects these particles around the planet, creating a teardrop-shaped bubble called the magnetosphere. It's like a cosmic windbreak, forcing the solar wind to flow around us rather than through us. The particles that do penetrate are funneled along magnetic field lines toward the poles, where they collide with atmospheric gases and create auroras. It's actually a beautiful system. Dangerous energy is redirected to the least populated parts of the planet and converted into a light show, nature's safety valve. But when the magnetic field strength drops to 6%, that windbreak becomes a screen door in a hurricane. Suddenly, solar wind particles aren't being deflected at 40,000 miles. They're penetrating much deeper, hitting the upper atmosphere with far greater frequency and intensity. And they're not just hitting the poles anymore. They're reaching mid-latitudes, even equatorial regions. The computer models created by the research team showed something remarkable and terrifying. During the Adams event, auroras would have been visible from everywhere on Earth, not occasionally, regularly. The night sky would have been alive with shimmering curtains of light that ancient humans had never seen before and couldn't possibly understand. Imagine being a Neanderthal in what is now France, stepping out of your cave at night and seeing the entire sky pulsing with green and purple waves. No scientific knowledge to tell you what's happening. No understanding of magnetic fields or solar wind. Just the visceral, primal knowledge that something is wrong with the world, that the sky itself has changed. Some researchers believe this might have influenced the sudden changes in cave art that occurred around this time. In caves across Europe, there's a noticeable shift in artistic style around 42,000 years ago. Paintings become more abstract, more symbolic. Handprints appear with increasing frequency, as if people were literally leaving their mark, asserting their presence in a world that suddenly felt less stable. But the psychological impact of strange skies was the least of humanity's problems. The real danger was invisible: radiation. When cosmic rays, high-energy particles from distant supernovae and other cosmic sources, hit Earth's atmosphere, they create cascades of secondary particles. It's like a cue ball striking a rack of billiard balls, setting off a chain reaction. These cosmic ray showers normally happen high in the atmosphere, about 30,000 to 50,000 feet up, safely above where anything lives. But when the magnetic field is weak, more cosmic rays get through, and they penetrate deeper. The radiation dose at ground level increases. Not to immediately lethal levels. We're not talking about instant radiation poisoning, but to levels that matter over time, especially for rapidly dividing cells, reproductive cells, growing embryos, young children. The research published in Science showed that during the peak of the Adams event, cosmic radiation levels at Earth's surface could have been 2 to 3 times higher than normal. That might not sound like much, but radiation effects are cumulative and multi-generational. Higher mutation rates mean more miscarriages, more birth defects, reduced fertility rates. Over generations, this creates demographic pressure that weakens populations and makes them vulnerable to other stresses. And there were plenty of other stresses. The ozone layer, that crucial shield in the stratosphere that absorbs UV radiation, began to deteriorate under the cosmic ray bombardment. Cosmic rays trigger chemical reactions that break down ozone molecules. As ozone levels dropped, More UV radiation reached the surface. UV radiation damages DNA directly. It causes mutations. It triggers cancers. It damages plant tissues and disrupts photosynthesis. The models showed that UV levels during the Adams event could have increased by 10 to 15% at ground level. That's significant. Modern humans worry about a few percentage points of ozone depletion causing increased skin cancer rates. Imagine 15% more UV, sustained for centuries, affecting everything from humans to crops to the plankton at the base of the ocean food chain. But perhaps the most insidious effect was what the increased cosmic radiation did to Earth's climate system. This is where things get really complicated, because we're not just talking about radiation exposure anymore, we're talking about fundamental changes to how Earth's atmosphere works. Cosmic rays influence cloud formation. When a cosmic ray particle enters the lower atmosphere, it ionizes molecules along its path, creating charged particles that act as condensation nuclei, seeds around which water vapor can condense to form cloud droplets. More cosmic rays mean more cloud condensation nuclei. More nuclei mean more clouds, and potentially brighter clouds that reflect more sunlight. This isn't just theory. Scientists have observed correlations between cosmic ray intensity and cloud cover in modern data. During the Adams event, with cosmic ray intensity 2 to 3 times higher than normal, cloud cover would have increased significantly. And more clouds mean Earth's albedo, its reflectivity, goes up. More sunlight gets reflected back into space instead of warming the surface. The result? Cooling, significant, rapid cooling that shows up clearly in the paleoclimate record from this exact period. Climate scientists have a term they use when describing the worst-case scenarios: cascade failure. It's what happens when one system fails, causing another to fail, which causes another to fail, until the entire interconnected web of Earth's climate system starts coming apart at the seams. That's essentially what happened during the Adams event. Let's start with the cooling. When cloud cover increases and more sunlight gets reflected away, temperatures drop. But Earth's climate doesn't just uniformly cool like turning down a thermostat. It's far more chaotic than that. Some regions cool more than others, weather patterns shift, ocean currents change, and all of these changes feed back into each other, amplifying the disruption. The paleoclimate data from this period, extracted from ice cores, lake sediments, cave formations, and ocean floor samples, shows dramatic and rapid changes. We're talking about temperature swings of several degrees Celsius happening over just a few decades. In climate terms, that's blindingly fast. In Greenland ice cores, the period around 42,000 years ago shows what's called a stadial, a cold period within the last ice age. Temperatures dropped suddenly. Snow accumulation patterns changed. The isotope ratios in the ice, which act like ancient thermometers, reveal rapid cooling, followed by unstable fluctuations. But it wasn't just getting colder. The climate was becoming unstable, unpredictable, chaotic. Some regions experienced drought, while others got increased precipitation. Monsoon systems, which billions of organisms, including humans, depend on for seasonal water, weakened or shifted their patterns. In Europe, the archaeological evidence shows that forests changed composition during this period. Cold-adapted species like spruce and pine expanded, while temperate species retreated. This wasn't a gradual transition over thousands of years. It happened in centuries, maybe even faster in some regions. For the animals living in these forests, and for the humans hunting those animals, this meant rapid habitat disruption. Prey species would have migrated to track their preferred environments. Predators would have followed, and humans sitting at the top of the food chain but utterly dependent on the productivity of the ecosystems below them would have felt every ripple of this disruption. The cooling also affected ocean temperatures and currents. The world's oceans are the great thermal regulators of Earth's climate. They absorb heat from the equator and transport it toward the poles through massive current systems. When ocean temperatures change, these currents can shift or weaken. Evidence from ocean sediment cores shows that the North Atlantic circulation, the system that includes the Gulf Stream, which keeps northern Europe habitable, experienced significant disruptions during this period. When this circulation weakens, it creates a cascade of effects: colder winters in Europe, changes in precipitation patterns across the Atlantic basin, disruption to marine ecosystems. And here's something that keeps climate scientists up at night. These circulation changes can happen remarkably quickly. The paleoclimate record shows instances where major ocean current systems have shifted in less than a decade. One year you have relatively stable climate. 10 years later, everything has changed. For ancient humans living in coastal areas or depending on marine resources, these changes would have been catastrophic. Fish populations would have shifted. Shellfish beds might have failed. Seabirds that nested on cliffs and provided a reliable food source might have moved to different regions. But the climate chaos wasn't limited to temperature and precipitation. Remember those increased lightning storms we talked about in Chapter 1? They had consequences beyond just starting fires. Lightning produces nitrogen oxides, chemicals that play a crucial role in atmospheric chemistry. Under normal circumstances, lightning-produced nitrogen oxides contribute to the nitrogen cycle, actually providing nutrients that eventually make their way into soils and oceans. But when lightning frequency increases dramatically, as it did during the Adams event, you can have too much of a good thing. Excessive nitrogen oxides in the atmosphere react with other compounds to form acids. Acid rain becomes more frequent and more intense. This damages vegetation, acidifies lakes and soils, and disrupts aquatic ecosystems. The effects cascade through food webs, affecting everything from insects to fish to the animals that eat them. The computer models of the Adams event showed that lightning frequency could have increased by 50% or more during the peak of the magnetic field collapse. That's a massive change. Wildfires would have been far more common. Landscapes that normally burned every few decades might have been burning every few years. This would have fundamentally altered ecosystems, favoring fire-adapted species while pushing out those that couldn't tolerate frequent burns. For human populations, this created a landscape of instability. Traditional hunting territories might become unusable due to fires. Water sources could be contaminated by ash. Medicinal plants or important food plants could be wiped out locally, forcing people to travel farther or learn to use different species. And then there's the megafauna extinction. Around the world, but particularly in Australia, large animals began disappearing from the fossil record right around the time of the Adams event. We're talking about creatures that had survived for millions of years through multiple ice ages and climate shifts. Giant wombats the size of cars, marsupial lions, enormous kangaroos standing 10 feet tall, massive flightless birds, an entire ecosystem of spectacular megafauna, all vanishing in what is, geologically speaking, the blink of an eye. For decades, scientists have debated what killed Australia's megafauna. Some blamed human hunting. Humans had reached Australia by at least 65,000 years ago, so they were certainly present. Others blamed climate change, pointing to the increasing aridity of the Australian interior. Still others suggested a combination of factors. But the timing has always been tricky to pin down precisely. Radiocarbon dating of megafauna remains suggested they went extinct somewhere between 50,000 and 40,000 years ago, a frustratingly wide range that made it difficult to identify a specific cause. Now, with the discovery of the Adams event and its precise dating to 42,000 years ago, that wide range suddenly has a bullseye in the middle of it. The extinction of Australian megafauna coincides almost perfectly with the period when Earth's magnetic field collapsed, cosmic radiation spiked, and the climate went haywire. Coincidence? It's possible, but it's starting to look less likely. Here's what makes mass extinctions so insidious. They rarely have a single cause. It's not usually one catastrophic event that wipes everything out. Instead, it's a perfect storm of stresses that push species past their breaking point. Think of it like this. Imagine you're trying to balance on a tightrope. you can handle a gentle breeze. You can handle the rope swaying a bit. You can even handle someone throwing light objects at you. But if all those things happen at once, wind picks up, rope starts swaying, and someone throws something heavy, suddenly you're falling. That's what happened to Earth's ecosystems during the Adams event. Multiple stress factors converged simultaneously, and species that might have survived any one of them couldn't survive all of them together. Let's look at the Australian megafauna more closely, because their extinction is one of the clearest examples of this multi-factor stress scenario. These were animals that had evolved over millions of years to thrive in Australia's unique environment. They'd survived the gradual drying of the Australian interior as the continent drifted northward. They'd adapted to nutrient-poor soils and irregular rainfall patterns. They were tough, resilient creatures finely tuned to their environment. But then several things happened at once. Human hunters arrived, adding a new predatory pressure that these animals had never experienced before. The climate became more unpredictable due to the Adams event, with increased droughts and fires. Vegetation patterns changed as plants responded to increased UV radiation and climate instability. And, subtly but significantly, the increased cosmic radiation may have affected reproduction rates and mutation frequencies. Large animals are particularly vulnerable during environmental stress because they have long generation times and small population sizes. A female giant wombat might not reach breeding age until 5 or 6 years old, and might only produce one offspring every few years. In stable conditions, this is fine. But when infant mortality increases due to environmental stress, when food becomes unreliable, when prime habitat shrinks, suddenly these slow-reproducing giants can't keep up with the losses. Add human hunting pressure on top of that, and you have a recipe for extinction. Humans don't even have to be particularly efficient hunters. If they're simply removing breeding age adults faster than the population can replace them, the mathematical outcome is inevitable. The population spirals downward until it hits a critical threshold, and then it collapses completely. The fossil record shows this happening not just to megafauna, but to many other species during this period. Medium-sized mammals that couldn't adapt quickly enough to the changing vegetation. Birds whose food sources disappeared. Reptiles whose carefully calibrated temperature-dependent reproduction systems got disrupted by the chaotic climate. But extinctions don't happen in isolation. Every species that goes extinct leaves a hole in the ecosystem. Remove a large herbivore, and suddenly the plants it used to eat grow differently. Remove a predator, and prey populations explode or shift their behavior. Remove a species that spreads seeds or pollinates flowers, and plant communities change. Every extinction sends ripples through the food web, creating new pressures on other species. Scientists call this an extinction cascade, and it's exactly what appears to have happened during the Adams event. The timing of extinctions across different regions and different types of organisms all cluster around this 42,000-year mark. It's visible in the data from Australia, from Eurasia, from the Americas. In Europe, large mammal populations declined dramatically. Species that had been common became rare, others disappeared entirely from regions they'd inhabited for hundreds of thousands of years. The archaeological record shows a noticeable decrease in the number of animal bones at human sites during this period, suggesting that game animals were becoming scarcer. This scarcity would have forced human populations to adapt. They would have needed to diversify their diets, hunt smaller animals, gather more plant foods, move more frequently to find resources. For populations already stressed by climate chaos and increased radiation exposure, these additional pressures would have been significant. And this brings us to one of the most intriguing aspects of the Adams event. It didn't just cause extinctions, it also drove innovation. The archaeological record from around 42,000 years ago shows something remarkable, a burst of technological and cultural innovation among Homo sapiens. More sophisticated stone tools appear. Bone tools become more common. Art becomes more prevalent and more complex. Long-distance trade networks expand. Symbolic behavior, the use of ornaments, pigments, and ritual objects, intensifies. Anthropologists have long noted this period as a crucial turning point in human cultural evolution. It's sometimes called the Upper Paleolithic Revolution in Europe or the Later Stone Age in Africa. It's when modern human behavior, as we'd recognize it, really crystallizes in the archaeological record. For years, scientists have debated what drove this cultural flowering. Was it a cognitive breakthrough, some change in human brain wiring that made us suddenly more creative? Was it population pressure forcing innovation? Was it contact between different groups, sharing ideas and technologies? The Adams event offers a new perspective. Maybe it was crisis-driven innovation. When the environment becomes unstable and unpredictable, when old strategies stop working, populations either innovate or die. The ones that figure out new technologies, new social structures, new ways of organizing knowledge and passing it on, those are the ones that survive. This is evolution in action, but it's not just biological evolution, it's cultural evolution, happening on a much faster timescale. And it's being driven by environmental pressure created by a cosmic event, the collapse of Earth's magnetic field. So we have this picture emerging. Around 42,000 years ago, Earth's protective magnetic shield failed. Cosmic radiation increased. Climate became chaotic. Ecosystems were stressed to the breaking point. Many species, including megafauna around the world, went extinct. Human populations declined and scattered. But some human populations, specifically Homo sapiens, responded to this crisis with innovation, developing new technologies and new strategies that not only helped them survive, but positioned them to eventually dominate the planet. Meanwhile, another human species, one that had survived for hundreds of thousands of years, that had weathered ice ages and climate shifts, that had a brain as large as ours and cultural sophistication, we're only now appreciating, was struggling, and ultimately failing. The Neanderthals were dying, and the Adams event might explain why. Let's talk about Neanderthals for a moment, because we need to stop thinking about them the way pop culture has portrayed them for the last century and a half. They weren't brutish cavemen. They weren't evolutionary dead ends too stupid to compete with our supposedly superior ancestors. They were humans, different from us, yes, but human in every way that matters. They had brains as large as ours, sometimes larger. They made sophisticated tools. They controlled fire. They cared for their sick and elderly. They buried their dead with what appears to be ritual and emotion. They created art. They made jewelry. They even interbred with Homo sapiens, which means if you're of European or Asian descent, you carry Neanderthal DNA right now, typically about 2% of your genome. These were people, and for over 300,000 years, they were successful people, thriving across Europe and parts of Asia, through some of the harshest climate conditions Earth has thrown at humanity. They survived the penultimate ice age. They adapted to rapid climate swings. They hunted woolly mammoths, cave bears, and other megafauna that would terrify most modern humans. They lived in landscapes where winter temperatures regularly dropped to -20 degrees Fahrenheit or lower, where blizzards could last for weeks, where simply surviving through winter required incredible skill and preparation. And yet, sometime around 40,000 years ago, they disappeared. The last Neanderthal populations clung on in isolated refuges, caves in Gibraltar, pockets in the Caucasus, scattered sites across southern Europe before finally vanishing from the fossil record entirely. Why? What happened to a species that had been so successful for so long? For decades, scientists proposed various theories. Maybe Homo sapiens simply outcompeted them. We had better technology, better social organization, better communication through more sophisticated language. Maybe we brought diseases with us from Africa that Neanderthals had no immunity to. Maybe we interbred with them so extensively that they were absorbed into the Homo sapiens population rather than going truly extinct. Maybe climate change during the last ice age made their preferred habitats uninhabitable. All of these factors probably played a role, but none of them fully explained the timing or the completeness of their disappearance. Neanderthals had survived previous encounters with Homo sapiens. They'd survived previous climate shifts. Why did this particular period, around 40,000 years ago, prove fatal? Enter the Adams event. When you overlay the timeline of Neanderthal extinction with the timeline of the magnetic field collapse, something striking emerges. The final decline of Neanderthal populations, the period when they disappear from most of their range and contract into those isolated refuges, happens right in the middle of the Adams event's peak impact period. This could be coincidence. In science, correlation doesn't automatically mean causation. But when you start looking at where Neanderthals lived and how they lived, a compelling case emerges for why the Adams event might have been particularly devastating to them while Homo sapiens managed to survive. First, let's talk about geography. Neanderthals were primarily adapted to the high-latitude environments of Europe and Western Asia. They'd evolved there over hundreds of thousands of years, developing stocky, cold-adapted body plans with short limbs and barrel chests that conserved heat. Their entire physiology was tuned for life in glacial and near-glacial conditions. During the Adams event, these high-latitude regions would have been hit particularly hard by the climate disruptions. Remember those weakened ocean currents we discussed? The North Atlantic circulation system that keeps Europe warmer than it should be for its latitude. That system was disrupted during this period, meaning Europe got even colder than it would have otherwise. At the same time, the increased cosmic radiation and deteriorated ozone layer would have had their strongest effects at higher latitudes. The Earth's magnetic field, even when weakened, still provides more protection at the equator than at the poles due to the geometry of the field lines. Neanderthals, living predominantly in Europe, were in one of the most exposed regions on the planet. But it gets worse for them. Neanderthals appear to have been specialized hunters, focusing heavily on large game. The archaeological evidence shows that Neanderthal diets were dominated by meat from large herbivores, deer, horses, bison, mammoths. Their entire lifestyle and culture was built around hunting these animals. Their tools were optimized for it, their social structures were organized around it. Their caloric requirements, which were high due to their muscular, cold-adapted bodies, demanded it. During the Adams event, those large herbivore populations were under severe stress. The chaotic climate meant unpredictable vegetation patterns. The increased fires destroyed grazing areas. The climate cooling and instability disrupted migration routes. Many of these large animals went extinct or saw their populations crash. For a specialized hunter like a Neanderthal, this was catastrophic. If your entire survival strategy is built around hunting mammoths and you've perfected this strategy over thousands of generations, what do you do when the mammoths start disappearing? You can't just suddenly become a generalist, eating a wide variety of smaller animals and plant foods. That requires different tools, different knowledge, different social structures. Homo sapiens, by contrast, appear to have been more flexible. The archaeological evidence shows that early modern humans had more diverse diets, including smaller game, fish, shellfish, and a wider variety of plant foods. When one resource became scarce, they could switch to others. This dietary flexibility would have been a crucial advantage during the environmental chaos of the Adams event. There's also the question of population size and distribution. By the time of the Adams event, Neanderthals were already a relatively small population scattered across Europe in semi-isolated groups. Genetic studies of Neanderthal DNA extracted from fossils suggest they had low genetic diversity and small effective population sizes, possibly just a few thousand individuals across their entire range. Small populations are vulnerable populations. They're more susceptible to inbreeding. They're more likely to be wiped out by local disasters. They can't afford to lose many individuals before facing a demographic crisis. And they're less likely to produce the rare innovations that might help them adapt to new challenges. Homo sapiens, meanwhile, had larger populations spread across a wider geographic range, from Africa through the Middle East and into Asia and Europe. We had more genetic diversity, more cultural diversity, more opportunities for innovation and adaptation. When one population struggled, others might thrive and eventually recolonize the struggling region. The end didn't come all at once for the Neanderthals. It came in waves like a slow retreat before an advancing tide. The archaeological record shows a pattern. Neanderthal sites across their range begin to thin out and eventually disappear, starting around 45,000 years ago and accelerating through the period of the Adams event. First they vanish from the northeastern edges of their range, then from Central Europe, then from most of France. By 40,000 years ago, they're essentially gone from most of Europe, hanging on only in a handful of refuges in southern regions. One of these final refuges was Gibraltar, that rocky promontory at the southern tip of the Iberian Peninsula where Europe nearly touches Africa. The caves there, Gorham's Cave in particular, have yielded some of the youngest Neanderthal remains ever found, dated to around 40,000 years ago, possibly even slightly more recent. Imagine what it must have been like to be among those final populations. Your ancestors had ranged across all of Europe, from the Atlantic coast to the Caucasus Mountains. But generation by generation, your world has been shrinking. Stories passed down from elders tell of lands to the north that your people no longer visit, of hunting grounds now empty or occupied by the strange, tall newcomers, the Homo sapiens with their different tools and different ways. The climate has become less predictable. Winters that your parents said were harsh are now even harsher. The herds of reindeer and horses that once migrated through your territory regularly now come less frequently or not at all. The sky sometimes displays colors at night that the elders say are new, omens of trouble. You've retreated to these coastal caves where the climate is slightly milder, where seals and dolphins sometimes beach themselves and provide easy meals, where shellfish can be gathered from the rocks. But even here, resources are stretched thin. Your group is small, maybe 20 or 30 individuals. You rarely encounter other Neanderthal groups anymore. Sometimes you see the newcomers, the Homo sapiens, in the distance. Sometimes they're friendly, willing to trade. Sometimes they're hostile. Mostly you avoid each other. But avoiding each other means your breeding population is even smaller. Your sister has no suitable mate within the group. 2 children born last year died before their first winter. The group's knowledge keeper, an old woman who remembered the hunting songs and the best places to find medicinal plants, died last spring, and some of that knowledge died with her. This is what geneticists call a death spiral, a population that has dropped below the minimum viable size. Even if nothing else goes wrong, even if the climate stabilizes and the game returns, you might not have enough genetic diversity to survive long term. Inbreeding becomes inevitable. Birth defects increase, infant mortality rises, the population contracts further. And then add on top of that baseline crisis all the stresses of the Adams event. Increased radiation affecting fertility and fetal development, climate chaos making food unpredictable, increased UV radiation causing health problems, the competition from Homo sapiens populations that seem better able to adapt to the changing conditions. The archaeological evidence from these final Neanderthal sites is poignant. The tool assemblages show a people trying to adapt, incorporating some techniques from Homo sapiens tools, experimenting with new designs. Personal ornaments become more common, as if symbolic behavior and identity became more important as the population dwindled. Some sites show evidence of more intensive processing of lower quality resources, cracking open bones to get at the marrow, eating animals that were previously ignored, but it wasn't enough. One by one, the last refuges went silent. The caves were abandoned. The hearths went cold, and by around 39,000 years ago, possibly 38,000, the last Neanderthals were gone, or were they? Here's where the story gets complicated, because Neanderthals didn't entirely disappear. They live on, in a sense, in us. That 2% of Neanderthal DNA in modern non-African populations isn't just random genetic noise. It's functional DNA that does things, influences our immune systems, affects our skin and hair, impacts how we respond to certain diseases, even influences some aspects of our behavior and cognition. This means that in the late stages of Neanderthal existence, as their populations were declining, there was significant interbreeding with Homo sapiens. Some Neanderthals, particularly females, based on the genetic evidence, were having children with Homo sapiens partners, and those hybrid children were being integrated into Homo sapiens communities. From a purely genetic perspective, this was probably the smartest thing the Neanderthals could have done. When your own species is facing extinction, getting your genes into a more successful species gene pool is a form of survival, even if it means your distinct population and culture disappears. But it's still tragic, because what was lost wasn't just a set of genes. It was an entire way of being human, a culture that had developed over 300,000 years. Languages we'll never hear, songs we'll never know, stories and knowledge and ways of relating to the world that disappeared forever when the last person who remembered them died. The Adams event likely accelerated this process. The environmental stresses it created pushed Neanderthal populations past their breaking point faster than might have otherwise occurred. The climate chaos compressed their habitat. The increased radiation affected their already fragile populations. The ecological disruptions eliminated their prey base. And perhaps most importantly, the Adams event created conditions where Homo sapiens, with our greater dietary flexibility, larger population sizes, and more diverse toolkit of survival strategies, had a decisive advantage. We didn't necessarily outcompete Neanderthals in direct confrontation. We just survived the cosmic storm better, and when it was over, we were still standing, and they weren't. Recent genetic studies have added another intriguing wrinkle to this story. Analysis of Neanderthal DNA shows signs of low genetic diversity and population bottlenecks that preceded their final extinction. In other words, they were already struggling before the Adams event hit. Their populations had been declining for thousands of years due to climate pressures and competition with Homo sapiens. The Adams event, then, might have been the final blow rather than the sole cause, the knockout punch delivered to an opponent already on the ropes. Without the additional stress of magnetic field collapse and all its consequences, perhaps Neanderthals could have recovered, rebuilt their populations, adapted to coexistence with Homo sapiens. But with that added cosmic catastrophe, they simply couldn't survive. So here we are, the descendants of the humans who survived the Adams event, looking back across 42,000 years at the cosmic catastrophe that nearly ended us and did end our closest relatives. But we shouldn't feel too smug about our ancestors' survival, because the uncomfortable truth is that Homo sapiens came very close to extinction as well. We just got lucky in a few key ways. The genetic evidence tells a sobering story. All modern humans outside of Africa descend from a relatively small founding population that lived through a series of bottlenecks, the most significant of which occurred right around, you guessed it, 40,000 to 42,000 years ago. The total human population might have dropped to as low as 10,000 to 30,000 individuals worldwide during this period. To put that in perspective, there are more people living in a single city block in Manhattan than comprised the entire human species during the worst of the Adams event. We were one bad break away from following the Neanderthals into extinction. What saved us? Partly luck. We happened to be more widely distributed geographically, which meant some populations were in refuges that weathered the storm better than others. Partly flexibility. Our more generalist diet and more diverse toolkit meant we could adapt to different resources when primary food sources failed. Partly innovation. The Upper Paleolithic technological revolution that occurred during this period gave us better weapons, better tools, and better survival strategies. But also, critically, we survived because of our social and cultural sophistication. The archaeological evidence from this period shows evidence of expanding trade networks, suggesting that different human groups were maintaining contact with each other, even across large distances. This meant ideas, innovations, and even genetic diversity could spread between populations. When one group discovered a better way to hunt or a new type of tool, that knowledge could spread to other groups. Neanderthals appear to have been more isolated, with less evidence for long-distance trade or contact between groups. This meant innovations stayed local, and struggling populations couldn't get help from more successful ones. In a crisis, connectivity is survival. The Adams event also appears to have driven significant cultural changes among the Homo sapiens who survived it. The humans who emerged from this crisis period were different from those who entered it. They had better technology, they had more complex social structures, they had more sophisticated symbolic behavior and art. They were in many ways recognizably modern humans, in a way that earlier Homo sapiens weren't quite. Some anthropologists now believe the Adams event might have been the crucible that forged modern human culture. The environmental pressure and population stress forced rapid innovation and cultural evolution. Groups that were more innovative, more cooperative, more able to share knowledge and adapt quickly, those groups survived, those that couldn't, didn't. It was natural selection operating not just on our genes but on our cultures. And here's where the story becomes urgently relevant to our modern world. Earth's magnetic field is weakening again. This isn't speculation or fear-mongering, it's measured fact. Over the past 170 years, the period for which we have detailed magnetic field measurements, Earth's magnetic field strength has declined by about 9%. The rate of decline is accelerating. The magnetic North Pole is moving faster than it has in centuries, currently shifting from Canada toward Siberia at an unprecedented rate. Some geophysicists believe we might be in the early stages of another magnetic reversal or excursion. Computer models suggest that at the current rate of decline, Earth's magnetic field could drop to crisis levels similar to the Adams event within the next few centuries or even sooner. Now, before anyone panics, we need to be clear, we're not facing the same existential threat our ancestors faced. We have technology they didn't have. We have global communication systems, early warning systems, the ability to track space weather and predict solar storms. We have infrastructure that can be hardened against radiation. We have medical knowledge to treat radiation exposure. But we're also more vulnerable in some ways. Our modern technological society depends on infrastructure that's exquisitely sensitive to electromagnetic disruption. Power grids, satellite systems, communication networks, all of these could be severely affected by the kind of solar storms that would become more frequent and intense if Earth's magnetic field weakens. Significantly, the Adams event gives us a preview of what happens when Earth loses its magnetic protection. It's not instantaneous apocalypse, but it is a cascade of environmental stresses that can push ecosystems and civilizations to the breaking point. Climate becomes more unstable. Radiation exposure increases. Infrastructure systems face unprecedented challenges, and unlike our ancestors, who numbered in the tens of thousands, we now have nearly 8 billion humans on this planet, most of us concentrated in cities, all of us dependent on complex global systems for food, water, and energy. We're incredibly powerful as a species, but we're also vulnerable in ways our ancestors weren't. The lesson of the Adams event isn't that we should fear magnetic field reversals. They're natural, inevitable processes that Earth has been through hundreds of times. The lesson is about adaptability, resilience, and the importance of understanding the cosmic context in which our civilization exists. Our ancestors survived the Adams event because they were flexible, innovative, and cooperative. They adapted their strategies when old ones failed. They maintained connections with other groups. They shared knowledge and innovations. They didn't give up when things got hard. They got creative. The Neanderthals, magnificent as they were, couldn't adapt quickly enough to a rapidly changing world. They were specialists in a world that suddenly demanded generalists. They were isolated when connectivity became survival. They were hit by a perfect storm of stresses, cosmic, climatic, ecological, and competitive, and they couldn't weather them all. As we face our own era of rapid environmental change, whether from magnetic field weakening, climate change, or other challenges, the Adams event reminds us that success isn't guaranteed for any species, no matter how intelligent or successful they've been in the past. Survival requires constant adaptation, cooperation, and the willingness to change strategies when circumstances change. The cosmic storm that struck 42,000 years ago killed the Neanderthals and nearly killed us. But it also forged us into something new, something more adaptable and resilient. The humans who emerged from the Adams event were tempered by crisis, shaped by adversity, and ready to spread across the entire planet and eventually reshape it. We are the descendants of the survivors, and that means something. 42,000 years ago, Earth's protective magnetic shield failed, and the planet was exposed to the full fury of cosmic radiation. The climate went haywire, ecosystems collapsed, species went extinct, and humanity, both Neanderthals and Homo sapiens, stood on the edge of oblivion. But we made it. Not all of us, the Neanderthals, fell, and their loss is a tragedy we're only now beginning to fully appreciate. But Homo sapiens survived, carrying forward not just our own genes, but also fragments of Neanderthal DNA, a living memorial to our lost cousins. The Adams event changed us. It forced us to innovate, to adapt, to become more flexible and more cooperative. The humans who emerged from that cosmic crucible were different from those who entered it. They were us, or at least the first recognizably modern version of us. Today, as Earth's magnetic field weakens once again, we face questions our ancestors couldn't have imagined. Can we protect our technological civilization from space weather? Can we adapt to rapid environmental change while maintaining the complex global systems that billions depend on? Can we learn from the past while building a resilient future? The Adams event offers both warning and hope. Warning, because it shows us how quickly a stable planet can become a chaotic one. Hope, because it proves that humans, adaptable, innovative, cooperative humans, can survive even cosmic catastrophes. We are still here because our ancestors refused to give up when the sky turned strange colors and the world became unpredictable. They adapted, they persisted, they survived, and so can we. The story of the Adams event is still being written by scientists around the world, piecing together evidence from tree rings, ice cores, fossils, and ancient DNA. Every discovery adds new details to our understanding of this cosmic catastrophe and what it meant for humanity's journey. If this story fascinated you, I'd encourage you to dive deeper. Look up the original 2021 research paper in the journal Science. Explore the work being done on Neanderthal genetics and what we're learning about our ancient cousins. Follow the research on Earth's current magnetic field changes and what it might mean for our future. And maybe, just maybe, the next time you see an aurora or look up at the night sky, remember that we live on a planet that's protected by an invisible shield generated by swirling currents of molten iron thousands of miles beneath our feet. It's protected us for billions of years. And when it failed, our ancestors survived anyway. That's the legacy we carry. That's the story written in our DNA. If you found this journey through deep time compelling, consider subscribing for more stories about the cosmic events that shaped humanity and the lessons they hold for our future. And share your thoughts in the comments. What aspects of the Adams event surprised you most? What lessons do you think it holds for how we face challenges today? Thanks for joining me on this journey through one of history's most fascinating and least known catastrophes. Until next time, keep looking up and stay curious about the cosmos that shapes our world in ways we're only beginning to understand.